Okay, it's time to do some testing once again on this pulse motor. If you haven't watched my previous video, I suggest you do so. This will show you how this is going to be hooked up, but we will go through it just quickly. We have our 24 volt battery bank. There's one battery, and we have 1, 2, 3 caps which are hooked up in parallel as our second battery. This cap here is the output storage cap, which will of course be going across our load, which is 3 red LEDs hooked in series. From the positive of a 24 volt battery, we're going through an LED here, which is the same as those 3. We are then coming out of that LED and we are going through this meter here, out of the meter back into the positive side of our cap bank, which of course is our second battery. On the output, we're coming out of the positive, we're going through this meter, back through the meter and through the 3 LEDs which are hooked in series, of course, back to the negative side of our output cap. I will be doing some scope shots, but I know when I convert the video the frame rate isn't going to be flash, so they're not going to look very good, so I will be doing a separate video in high definition of the scopes after this one. So the little bit of information: the circuit is a standard Ssg circuit. 2 differences to the way we normally do it. This coil is the very first coil I ever made for my very first pulse motor. It is actually wound wrong to how a standard Ssg coil is wound, but it actually works very, very well. The rotor has 8 magnets in it, and they are north, south, north, south, north, south alternating fields, which is also different than the standard Ssg. And you will see a very big advantage of doing it this way on the scope a little later. So the first thing we're going to do, what we're trying to achieve here, is to measure the input current of the machine, or the watts being consumed and the watts being given back. So like I said, we're coming off this 24 volt battery positive, going through this little LED and then back to the positive on this battery, which of course are caps. And with this setup, there is no resistors in the system whatsoever except for the coil, which we don't have to take into account because it is feeding from the caps, not the battery. The voltage across the system, or the current that's running through this LED, is the potential difference between the positive on this 24 volt battery and the positive on this cap, or this battery. As you would know, it is not going to be the current draw times 24 volts, or that LED would blow clean to hell. So we have another meter here. We will be measuring the voltage across this LED, which of course is from positive to positive, and we'll be measuring the voltage on the output cap so we can get a total watts output on that. We can get a total watts input on that. We're also going to test this input current in that when we start the machine, we should have a consumption through this LED before we get 3 LEDs to light up. Now, keeping in mind an LED is just a diode, you do get a voltage drop across them. With 3 hooked in series, that voltage drop is 3 times as much. We'll also be doing an instant stop test, where we instantly stop the flywheel, and in theory should take, if the machine is using more than it's giving, it should take longer to fill the caps back up to an equal voltage, or a voltage that the LED goes out or stops drawing current, which we'll see on that meter. So these three here should go out because we're running 3 times the load that we are with one LED. So in theory, current should still be flowing into these caps to fill them back up, and these should have well been gone out. So the first thing we're going to do is, of course, flatten this cap right out. We're going to empty it. So that cap, which is our output cap, is now flat, and we will put the meter across that just to confirm it. As you see, we have a little bit of recovery voltage, 87, 88 milliamps, millivolts, which, as you know, all caps do that. Three millivolts, 4 millivolts. So that cap is totally empty, which is our output cap. The input cap, or the input caps, come battery. We're going to start on full, or the same voltage as the battery, which we do simply by jumping the LED, because like I said, there will be a voltage drop of 1.5 maybe, or maybe even the 0.6 as a normal diode. I'm not sure, I've never measured the voltage drop across an LED. So okay, so what we're going to do is start the machine, and if it's consuming more current excuse me, than it's giving, then this LED here should light up before these three do. Now remember, we have to fill this capacitor from empty. So we will turn our meters on. Like I said, this one is the current across these three LEDs. This one is the current passing through this LED. So now we're going to start the machine, and you can keep an eye on the LEDs as well as the meter, and we'll see what happens. So as you can see right there, the output started way before the input did. We will now let the machine build up. Now if you've seen the previous video on the test we done on this, there was a pretty good discussion on it. At the time I was happy with what people had to say on what was actually happening, due to we had resistors in the way of incandescent bulbs and another resistor here, 37 ohm or something like that, and it was a consumption of power between the resistors and the machine itself. So we'll just measure the battery voltage at the moment. The batteries have 25.16, probably come down a little bit once the machine builds up, or not. So it's 25.16 volts in what we'll call battery 1, and at the moment in battery 2, which is our caps, we have 22.87, which will go down a little bit once the machine speeds up. So a potential difference between positive on our 24 volt battery and positive on our 22 volt battery at the moment is around 2.3 volts, 2.2, which of course will be the voltage across our LED. So we can pretty safely assume that 25 volts at 24 milliamps would blow that LED completely apart. And remember, we don't have to take any resistance encountered by the coil, because this coil is hooked directly to these three large caps, and that is where it's drawing its current from. The current flow through this LED is a very steady current flow, and we will see that on the scope very shortly. So to measure our output current, or watts, we know we're doing 35 milliamps, 7.66 volts. So of course we can calculate our output current by that. Our input current is not 26 milliamps at 25 volts. Our input current is 26 milliamps at 2.318 volts. Because as you know, that little 25 milliwatt LED will not handle whatever the wattage is between our 25 volts times our 26 milliamps, which is somewhere around 450 maybe. And like I said, they're identical LEDs. These three are hooked in series, so we have 3 times the voltage drop across those LEDs as we do this one, which is something to keep in mind. So the first thing we're going to do now, I might have to take you off the stand, which is a bit tricky. I bought one of them U-Boot magnetic stands so I could just sit the camera on and then take it off whenever I please, but as soon as I sit the camera on it, it turns off, so it was absolutely no good to us. Okay, now like I said, the scope shot's not going to look terribly good once I resize this video, and I will be doing it again, but you'll get a general idea. The first thing we're going to do is we're going to put the scope across our LED, just to make sure there is absolutely no pulsing across the LED, and that will show that the coil is not drawing the power from the 1 batteries, it is drawing it from the capacitors themselves. And this is a bit hard one-handed. So of course the positive side, or the probe, will go to the positive side, and the ground the negative side, even though it's positive on the cap, because that is the low point of the voltage. We are set on times 1. We are on the 5 volt divisions. Now if anyone wants to know what's going on with these knobs, the ones that used to be on it broke, and these are actually ones I bought at the shop in the pot, and I had to remark them because the screw that sits on the flat bit on the shaft is in the wrong position. As you can see, going all the way to what marks I've put on are indeed in the right spot. And same with our time divisions. So I'll set it on 1 volt. And these little purple marks are, this fell off the block. Squares that are on the inside of that, whatever it is, drop down, and the squares on the outside they're about halfway in between them now, so I have to take the scope apart and try and line them back up. But I'm going to use this purple mark here, the big one, as our 0 volt line. That's as close as I could get it. So we'll zero it out there, hit that. We are on the 5 volt divisions, so you can see there is about 2.5 volts across our LED. So as you can see, the line is very smooth. We will go up to the 2 volt divisions, 1 volt divisions, half volt divisions, and the line is very smooth still. So we have no ripple across the LED, or no spikes, which means our motor is pulling from the caps, which of course are the lowest point of resistance. The other reason I know is because I can disconnect the power from the machine and it still keeps going. So what we're going to do now is we're going to take the probe and put it on the positive side of our run coil, and the ground we're going to put on the negative side, and we can see exactly what's happening inside that coil. And this is where it gets a little spinny. And we'll also be able to see the power consumption and what it's giving back. So first we'll hit 0, make sure our line is zeroed out, and of course most of the time pulse motors, you'll see it all happening, all the current, everything will be of course on the plus side of our 0 volt line. So let's have a look. Look at that. There we go, that's better. So let's see what's happening here. There is the current being created by the magnet, which is north leaving the coil and south approaching the coil, and then you will see the transistor switch on, just over a volt. Sorry, trying to do this one-handed. And as you'll see right up the top here is the time our transistor is on, but in between there is no current being pulled by the coil. Most of the current is below the 0 volt line, and we are getting this because instead of there being a north field from the permanent magnets in the rotor creating a back EMF against the coil, when the transistor fires we have a south field. If we have a north field, that's when you create current, because you're trying to build an opposing field in the coil against that north magnet, which creates a back EMF, which of course we need current to do. When the coil has a south magnet in front of the core, you don't get any back EMF because they're attracting, so it takes very little current, as you can see. There's probably 3 volts in the coil, and then there is just about absolutely no current draw or whatever to get the coil up to the 12 volts. Now I'm pretty sure with a bit of tuning, using a small capacitor and a resistor, I can get that on time down even smaller. So now what we want to see is the current that is going into our charge cap. And the way we can do that quite easily is we simply put the earth or the ground of our scope on the positive side of our run coil and the probe on the negative side. So now everything that is above the 0 volt line is current that we are sending back to our charge cap, and as you can see there's a whole lot more current above the 0 volt line than we are using below. The darker the lines on each oscillation, the more current we use or we have, and that's because it's volts over time equals current. So you can't see any current on the bottom side at the moment because the time to get it up to the 12 volts, thanks to our south field on the rotor, is very little. Now, at the moment on our 5 volt divisions we have about 7.5 volts or 8 volts that is going back to the collector, which of course is a positive charge because we have these two swapped around through our diode and in here. So like I said, that's about 8 volts, and that's what we should have in our large cap. Of course, minus the voltage drop from the diode, and we'll take the leads off the flywheel, that always helps. And as you can see, we've got 7.68 volts in our capacitor, which is running those 3 LEDs at 35 milliamps. This meter has timed out and 37. So what we can do to confirm that is the voltage or the current that's going into our cap is I'm going to pull one of the leads out so we don't draw a load off it. The voltage in this cap of course should go up, and of course so should our lines here. So I'm going to do this one hand and to pull out the negative side now, and you can see the voltage climb. Plug it back in, it goes down. Pull it out, it climbs. Along with that, pull it out, it climbs. Plug it back in, it goes back down. So as you can clearly see in the scope, we have a lot more current going to the output cap than we are using to get our run coil up to the 22 odd volts that's in the caps. So I'll just put this back around the other way so the probe is on the positive of our run coil. And if we count our divisions, 5, 10, 15, 20, and you can see we're at about 22 volts, which should be the voltage that's in our run caps around about. She's 22.77. So now what we're going to do is an instant stop test. Oh, there was one other thing. Take a good look at that across the run coil. So what we're going to do now is put this across the trigger coil. And it's almost identical, other than the current being a little stronger on the top and the bottom, and it's because of our resistor going to the base. So we'll disconnect that, get it out the road, Now what we're going to do is, this is going to be a bit tricky, try and hold it with that, so I might have to try and put it back on the stand, which is a mongrel because the bolt on the stand doesn't like going in the camera too easily, so bear with me. And look at that, I've got it first pop. So if we're actually using more current than we're putting out, if I stop that flywheel, which stops the system instantly, it should take a longer time to replace that current we've used in 3 caps then these 3 LEDs will consume the current from that 1 cap. So we can keep an eye on the milliamps. Like I said, this is for these 3 LEDs. This is the current across that 1 LED. So we're going to stop the machine instantly. Now these 3 LEDs should burn up all our available current a whole lot quicker than what it's going to take the current to pass through this 1 LED and replace the energy that the system is using. So like I said, we can keep an eye on the LEDs and we can keep an eye on the current when I stop the machine. So here we go. Look at that, exactly the same. So we burnt 3 LEDs at a higher wattage than we did the 1 LED took to fill the caps back up with the current that we consume. And remember, we have 3 times the voltage drop across those 3 LEDs than what we do across 1. So like I said, next I will do a high definition video purely on the scope shots, because I know you're not going to be able to see them too clearly. The frame rate is 50 frames per second and our power supply happens to be the same, so there will be some sway between the two because they won't be exact. Okay, well that's it from me. Cheers from the Tin Man.